Recording is going. So looks like everything's working the way it should. Okay, so today we are going to start section 11.1. And that will cover parametric equations. Okay. So here we'll kind of introduce you to parametric equations. If you're going into Calc 3, they'll dive a little bit deeper into them. Okay. With parametric equations, if you remember, one way to look at it is if you remember the definition of a function is only defined if it passes the horizontal line test. The vertical line test. One-to-one function is a horizontal line test. So if you're dealing with a function, you're fine because it passes the vertical line test. But what if you have one that does not pass the vertical line test? Well, this is where the parametric equations come in, because then you can still do everything with them that you could do with a regular function without breaking any laws of math. So parametric equations are useful when describing curves on a plane that may or may not be defined as functions. So they work with functions and they work when it's not defined as a function. Okay, now parametric curves in order to be able to graph them when they're not defined as a function means they have to have some sort of direction. So they have a direction, and that direction is we're going to let x equal some function f of t. And we're going to let y equal some function we'll call g of t. And that f of t and g of t, those are your parametric equations. So all we're doing is we're introducing a third variable, so we'll be able to graph and calculate and everything else that you could do with a defined function. And that third variable, in this case t, that is called your parameter. the parameter in parametric equations. Okay. So let's say, for example, if we have just a regular, ordinary defined function, okay, just some random function. And we know it's a function because it passes the vertical line test. Any vertical line will only pass through that graph once. Okay, and this is just a defined function. Okay. Now, what if we have a graph that does not follow the actual definition of a function? So let's say if we have some graph, let's say it looks like this. See there, it fails the vertical line test and probably in a few other places, depending on how many times it swings around. Okay. So let's say for some value x, that might be right here. Well, we can't say, well, when x is equal to 4, y is equal to 7. Well, we can't say that because y could be equal to 7, 12, 25, and a bunch of other values that would make it an undefined function. Well, not a function at all by definition. But we can bring along a third variable and say, okay, when t is equal to 0, our graph is right here. When t is equal to 1, we're right there. When t is equal to 2, we're right there. We can call that t number 1, t number 2, t number 3, and keep on going all the way till we reach the very end. We'll say, okay, our very last t could equal 15 or whatever it is. Okay, so this will allow us to graph functions, well, not graph functions, but graph shapes for expressions that aren't defined as functions. Okay, so we know that as our parameter t changes, every point on here that normally for a function would be xy becomes f of t, g of t. And all of those changes to our parametric curve. Excuse me. right. Okay, so let's say, for example, if we wanted to sketch the curve, defined by the parametric equations, x is equal to 1 plus the square root of t. Y is equal to t squared minus 4t. And the parameters from t equals 0 to 4. So the best way to approach this until you get used to it is to start with what is called a t-chart. And that's just where we plug in our values of t. Okay, so we plug in our values of t. And because we have that square root, I'm only going to use perfect squares. So I'm only going to use 0, 1, and 4. But you can plug in any value you like. I'm just using those to make it easier. And then we have x is equal to 1 plus square root of t. And we have y is equal to t squared minus 4t. Give that a little more room. And after you plug in your t values, you will have your x and y ordered pair. Because this is your f of t, and this is your g of t. And make that squared a little bit neater than that. T squared, there we go. Okay, so this one, t is equal to 0, that gives us x is equal to 1 plus the square root of 0, which is just 1. And for here, t equals 0, so we have y is equal to 0 squared minus 4 times 0, which is 0. Straighten that up a little bit. So when t is equal to 0, our ordered pair is 1, 0. Okay. So when t is equal to 1, we have x is equal to 1 plus the square root of 1. Well, square root of 1 is 1, so 1 plus 1 is just 2. And here, when t is equal to 1, we have y is equal to 1 squared minus 4 times 1, which is 1 minus 4, which gives us negative 3. So that ordered pair is 2, negative 3. Same thing with t equals 4. X is equal to 1 plus the square root of 4. Well, square root of 4 is 2, so 1 plus 2 gives us 3. Here, if we plug in t is equal to 4, we have y is equal to 4 squared minus 4 times 4. 4 times 4. So that gives us 16 minus 16, which is 0. So we have the ordered pair 3, 0. Okay. So from there, we just sketch it the same way we would a function. Okay. So we know at the point 1, 0, that's where t is equal to 0. Bring that down a little bit more. At t is equal to 1, we're at the point 2, negative 3. So say 2, negative 3 is right here. So this is 1, this is 2, and we'll make this 3. And move that over so it's not in the way of the graph. 3. Okay, so at the point 2, negative 3, that's where t is equal to 1. And when t is equal to 4, our ordered pair is 3, 0. This is where t is equal to 4. So if you plug in all the values in between, really this would just kind of look like that, give or take. It's kind of a portion of a quadratic function, which is perfectly okay because you can use it on functions and expressions that don't define as functions. Now, the main difference is this has the direction from t equals 0 to t equals 4. So we know that as t increases, the curve actually moves in the direction of the arrows. All right, any questions on that one? All right. go. So let's say, for example, we wanted to determine a pair of equations that can parameterize the curve negative 7x to the fourth power is equal to negative x minus 4y plus 7. Make that y a little neater. Here we go. Using the fact that we know that x of t is equal to t minus 6 as one of the equations. And remember, they could say x of t or just plain x is equal to this, same thing. Okay, so all they're saying is they want you to parameterize it, is they want you to turn this equation into an equation using just the parameter t. Okay. So it's given that x of t is equal to t minus 6, which we can also rewrite as just x is equal to t minus 6. Okay, so x is already a function of t. So in this one, x is already equal to some function g of t. Or I'll call this one f of t and then call the y one the g of t, just to stay, it doesn't matter, but just to stay consistent. Okay, so now we have to convert y to a function of t. Okay, so to do that, first thing we're going to do is solve for y. So if we have negative 7 x to the fourth power is equal to negative x minus 4y plus 7. First thing we have to do is add x to both sides, where those two will cancel each other out. And next, we're going to subtract 7 from both sides, where those two cancel out. Make that a little clearer. There we go. So that gives us negative 7x to the fourth power plus x minus 7 is equal to negative 4y. So we divide each term by negative 4. The negative 4s cancel each other out. So we have y is equal to negative divided by negative is positive. And since they're all over negative 4, actually we'll make them over positive 4. So we just say y is equal to 7x to the fourth power minus x plus 7 all over 4. Okay, so we can see here that y is still a function of x. So we see that y is now a function of x. But we know that x is a function of t. So that means all we have to do is replace x with t minus 6. I'll just put x equals t minus 6. Oops. Okay. So that means our x of t, or just x, however way you want to put it, is t minus 6. Remember, that's your f of t. And your y that you want to make as a function of t, since y is right here, we can just make that, instead of negative 7 or 7x to the fourth power, we can make that 7 times t minus 6 to the fourth power. And instead of minus x, we can just say minus t minus 6 plus 7 divided by 4. So we now have our parameterized functions. I mean, not functions, parameterized terms. So negative 7x to the fourth is equal to negative x minus 4y plus 7 is now parameterized. Both are written as functions of t. Excuse me. Okay, so this is useful if they happen to give you one of the parameterized functions, but even if they don't give you one of them, it's still pretty much the same process. So let's say, for example, if we know that the curve let's say 3y squared is equal to x plus 4y minus 8. We want to know is that they are correct. Well, it is correctly parameterized by what pair of equations? Okay, so all this is saying is that they want you to write x and y as parameterized equations. Okay, so all you have to do for your first step is just solve for either one of the variables. Doesn't matter if it's x or y. For this one, we'll solve for x. And the only reason I picked x is because x here is by itself, so it'll be a little bit easier. Okay, so let's say for this one, we're going to solve for x. Okay, and again, just a little side note as to why I picked it. You can solve for either variable, so either x or y, but x is already isolated, making it easier. Again, the name of the game is to make it as painless as possible. So that 3y squared is equal to x plus 4y minus 8. We're going to subtract 4y from both sides. And we're going to add 8 to both sides, where those are going to cancel out. Okay, so now we know that x is equal to 3y squared minus 4y plus 8. So to turn this into a parameterized equation, or in other words, to make x equals some function of t, the fastest way to do that is to just make y equal t. That means that x is equal to 3 times t squared minus 4t plus 8. So that's your f of t. And we already made y equal t. And that's your g of t. Or you can say x of t is equal to this and y of t is equal to t. But I usually just leave it as the x and the y, unless I'm going to do something special with it. All right, so any questions on that one? Okay. Okay. So let's say if we wanted the curve, oops, make that a little bit neater. 3x to the 4th power is equal to y minus 5x squared minus 3 is correctly parameterized by what pair of equations? Okay, so again, you want to make it as pain-free as possible. And we can see here that the y is already isolated. So here we're just going to solve for y because it is already isolated. So it does not matter which one you solve for first. Just make it as easy on yourself as you can. So we have 3x to the fourth power is equal to y minus 5x squared minus 3. So we're going to go ahead and add 5x squared to both sides. And we're going to add 3 to both sides. That means we have y is equal to 3x to the fourth power plus 5x squared plus 3. So now we do the exact same thing. So to make y some function of t, we just replace x with t. That means that y is equal to 3 times t to the fourth power plus 5t squared plus 3. So we wrote that now as some function of t. And we know that our x is just equal to t. All right. Say, for example, suppose that an object moves from the xy coordinate for -9 to the coordinate -6, -5. And we know that these coordinates are in yards and takes 10 minutes to travel from one point to the other. Okay, so we want to give the parametric equations. With respect to the parameter t for the position of the object. Okay, so first thing we're going to do is look at our change in x. Which you can just look at it as x number 1 minus x number 0. So we have our 4, -9 to -6, -5. That would be our x0, y0, and our x1, y1. Okay. So we can see that this is just -6 minus 4, which is -10. So we can see here that it took that x value to go -10 yards in 10 minutes. Which means that x value changed at a rate of -1 yards per minute. Okay. So see here, this is our rate of change. Well, you can say of or for our x. So if it's the rate of change, then it's also the slope. So you can rewrite x is equal to some slope, and we'll say m number 1 because we're going to use the same thing for, say, m number x, just to keep it, say, slope of x. That's a little bit easier. Plus your x of 0, because that's your initial point when t is equal to 0. Okay, so we can see here that if this is our slope, we say x is equal to -1 times t. And when t is equal to 0, that should put you right at your starting point. It should be +4. T equals 0, x is equal to 4. Okay, so we want to match up with our initial point. Okay, and we do the exact same thing, but we find the change in y. Okay, and that change in y, just say your y number 1 minus y number 0, or your initial value of y. So that gives us -5 minus -9. Which is equal to +4. So we know that that y value, when a distance of 4 yards, in that same 10 minutes. Which means it went 2/5 yards per minute, which is the rate of change of our y. Oh, forgot to put my t right there. It's be the slope times t plus x of 0. And same thing for y. Y would be the slope of y, or the rate of change for y, times t plus y sub 0. So we can write y is equal to the rate of change, or the slope, 2/5 times t. And our initial y value is -9. So it should be -9. So we know that when t is equal to 0, your y has to be -9. That's just one way to double check it. All right, any questions on that one? Excuse me. Okay, so we looked at how to convert or add a parameterized equation. Now we're going to look at how to eliminate the parameters. Oh, P-A-R-A. Okay, now with this one, you can just use eliminating the parameter to change your two parameterized expressions into one regular Cartesian or rectangular expression or on the XY axis. Okay, so you have the option of replacing the X or the Y in one of your parametric equations. To convert them to a single Cartesian equation. And that's just an equation that appears on the XY axis. Okay, so let's say if we wanted to sketch X is equal to the square root of t, and Y is equal to 1 minus t by eliminating the parameters. Okay. So with me, the first thing you want to do is you want to pick either X or Y and solve for t. Okay. You can pick either one, but I'll just pick X is equal to the square root of t. Because one simple step, all we have to do is square both sides. And we know that t is equal to x squared. Oops. Okay, so all you have to do from there is just replace t with x squared in your y equation. I'll move that a little bit lower. So that means that our y is equal to 1 minus t. That just becomes y is equal to 1 minus, and that t just becomes x squared. So if we graph that one, then our graph will look something like this. You can say negative x squared plus 1 if you want to. And we know that x squared flips and it goes up 1. So it should look something like that one. So if you were to plug in values, t equals 0, t equals 1, t equals 2, it would be the exact same graph. The only difference is when you're using the parameter, it has a direction. But the graph itself looks exactly the same. All right, any questions on that so far? All right. Okay, so let's say if we have x is equal to negative 10t plus 11. Instead of x, let's switch it up and say x of t. Just to change it up a little bit. So let's say x of t is equal to negative 10t plus 11. And y of t is equal to 50t minus 6. We want to eliminate the parameter. To write the parametric equations as a Cartesian equation. And remember, that's also just known as a rectangular equation. So if you see a rectangular equation, same thing. Because your xy axis is called either the rectangular plane or the Cartesian plane, depending on who you ask. Okay, so just like before, pick either one of those and solve for t. And here we go. So we know that x is equal to negative 10t plus 11. I'm going to go ahead and subtract 11 from both sides. So we know that x minus 11 is equal to negative 10t. So go ahead and divide each term by negative 10. You know that those two are going to cancel each other out. That means our t is equal to x over negative 10, which just write it as negative 1 over 10 x plus 11 over 10. So now we just replace t in the other equation. So if you solve for y, you'd replace t in x. Not solve for y, but solved it for the y. And the remaining equation. So we know here that y is equal to negative 50t minus 6. Make that t a little bit neater. So we're going to replace that t with negative 1 over 10x plus 11 over t. So y is equal to negative 50 times negative 1 over 10x plus 11 over 10. So we can go ahead and distribute that negative 50. That gives us y is equal to negative 50 times negative 1 over 10 is positive 50 over 10, which is just positive 5 times x. Oh, did I add another? But I swear, I don't know why I do that. Just add random negatives everywhere. That should be positive, so it should be negative here. So I was thinking that this should be negative 5 and ended up writing the negative right there. That should be negative 5x. Plus, we have 55 over 10. No, not 500. No, 50 times 11 over 10. We can actually cancel out the 10. So that gives us 55 minus that 6, which should be right there. So if we get our 55 minus 6, I'll just actually write it out. And we can go ahead and combine those two. We have y is equal to negative 5x plus 49. All right. Any questions on that one? Okay. So what if I can ever get this paper separated? Let's say if we wanted to write the parametric equations. Say x of t is equal to the natural log of 9t, and y of t is equal to 5t. As a rectangular equation, by eliminating the parameter. Now you could solve for t for x or y. I'll just pick x for no specific reason, even though that one would be a lot easier. So we have x is equal to natural log of 9t. Okay. So here we're just going to raise both sides to e. So that gives us e to the power of x is equal to e to the power of natural log of 9t. Okay, so we have e to the power of x is equal to, remember that e to the power of natural log of x is just equal to x. So that means e to the power of natural log of 9t is just equal to 9t. So if we divide both sides by 9, we know that t is equal to e to the power of x over 9. And then from there, we just substitute. So if y is equal to 5t. That now becomes y is equal to 5 times e to the power of x over 9. Or you can just write that as y is equal to 5 times e to the power of x over 9. All right. Anyone still writing? Okay. So what if we wanted to write the parametric equations? Say x is equal to e to the power of 9t minus 6, and y is equal to e to the power of 8t minus 10 as rectangular or Cartesian equations, also known as Cartesian equations. Oh, as A. Okay. So both of these are pretty similar, so it doesn't matter really which one we pick first. Let's say x is equal to e to the power of 9t minus 6. Okay. So first we have to isolate that parametric term, in this case e to the power of 9t. So we just add 6 to both sides. So we know that x plus 6 is equal to e to the power of 9t. Now for this one, just like the last example, we knew that e to the power of natural log of x would equal x. But for this one, we have to know that the natural log of e to the power of x is equal to x. So just a little bit of a intermediate algebra slash pre-calc slash college algebra, whichever course you came from. They kind of went over this, but it's really easy to forget if you don't use it a lot. So that means we have to apply natural log to both sides. So that means we have the natural log of x plus 6 is equal to the natural log of e to the power of 9t. So our natural log, and they'll probably want that absolute value, but x plus 6, so we'll put it as absolute values. Unless they specify that x is greater than 0, they'll want the absolute value. So you have the natural log of x plus 6 is equal to the natural log of e to the power of 9t is just equal to 9t. So if we divide both sides by 9, we know that t is equal to the natural log of x plus 6 divided by 9. So now all we have to do with this one is substitute in our other equation. So the other equation is y is equal to e to the power of 8t minus 10. Well, we replace t, that gives us y is equal to e to the power of 8 times the natural log of x plus 6 divided by 9 minus 10. Well, we can factor out that 1/9 in the denominator. So we have y is equal to e to the power 8 over 9 times the natural log of the absolute value of x plus 6 minus 10. Okay. Now for this one, we're not done yet because we can still simplify it. But to do that, we have to remember our rules for logarithms. And for this one, we're going to need to memorize the power rule for logarithms. Okay, and that rule states that if we have the natural log of some argument raised to the power that we will call the power of exponent p, and by the power rule, that exponent moves down and becomes the coefficient times the natural log. We don't even need that parenthesis there. Times the natural log of our argument m. And let me kind of separate that a little bit. There we go. Okay. Well, the thing is, this rule works both ways. You can take the coefficient and move it up and make it the exponent. So that means we can write this as y is equal to the natural log of the absolute value of x plus 6 to the 8/9 power minus 10. Oh, forgot my e. So y is equal to e to that power minus 10. Okay, so now that we're here, we know that this means that we just have to use that. E to the power of natural log of x is equal to x. So that means e to the power of the natural log of x plus 6 to the 8/9 power is just x plus 6 to the 8/9 power minus 10. So again, if they say that x is greater than 0, then you won't need the absolute value. And sometimes they'll take it without the absolute value, but sometimes they will want the absolute value. So, like I said, all depends on the question. All right. Any questions on that one? All right. Excuse me. All right. So what if we wanted to write the parametric equations say x of theta is equal to -9 times sine of 2 theta, and y of theta is equal to -9 times cosine of 2 theta as a rectangular equation by eliminating the parameter theta. Okay, so sometimes they'll switch it up and the parameter will be something other than t. Okay, so for this one, probably the easiest approach is to remember that sine squared plus cosine squared is equal to 1. Okay, so first thing we have to do is we have to isolate our sine and cosine for that to actually help us. So if we have x is equal to -9 times sine of 2 theta, if we divide both sides by -9, we know that x divided by 9, and move that down a little bit, have a little more room between it. Negative x divided by 9 is equal to sine of 2 theta. And we do the same thing with y. We know that y is equal to negative 9 times cosine of 2 theta. So if we divide both sides by negative 9, we know that negative y over 9 is equal to cosine of 2 theta. Clean up that theta a little bit. It was a little messy. There we go. Okay, now since we know that sine squared of theta plus cosine squared of theta is equal to 1, if theta just represent our angle, then 2 times an angle is still an angle. So that means sine squared of 2 theta plus cosine squared of 2 theta is equal to 1. Now, if you wanted to, you could always rewrite that. Instead of sine squared of 2 theta, you could rewrite that as sine of 2 theta squared. And that cosine squared of 2 theta, you could rewrite that as cosine of 2 theta squared. Well, we know one thing about sine of 2 theta, and that's that sine of 2 theta is equal to negative x over 9. So if we replace that, that now gives us negative x over 9 squared. And that cosine of 2 theta, well, we know that cosine of 2 theta is equal to negative y over 9. So that's plus negative y over 9 squared. So equals 1. So if we get negative x over 9 times negative x over 9, negative times negative is positive, so we get positive x squared over 81. Plus negative y squared over 9 just gives us positive y squared over 81, which is equal to 1. So we can go ahead, if we multiply each term by 81, that'll simplify it a little bit more. Okay, so multiply this term by 81, the 81s cancel out, leaving just x squared. Plus, multiply this term by 81, the 81s cancel out, leaving just y squared. Multiply this term by 81, 1 times 81 is 81. So if we subtract y squared from both sides, that gives us, well, x squared from both sides. That gives us y squared is equal to 81 minus x squared. And make a little side note. Subtract x squared from both sides. And then here, all we have to do is square root both sides. And if you remember with the square root property, don't forget your plus minus. So if we square root both sides, that gives us y is equal to plus or minus the square root of 81 minus x squared. All right, any questions on that one? Right. Okay, so let's say if we wanted to write the parametric equations say x of theta is equal to 3 times secant of 4 theta, and y of theta is equal to 3 times tangent of 4 theta. You want to write it as a rectangular equation by eliminating the parameter theta. Excuse me. Okay. So just like before, whenever you're dealing with trig parametric equations, you want to remember that sine squared plus cosine squared is equal to 1. But since we're dealing with secant and tangent, you want to take that sine squared plus cosine squared is equal to 1 and divide each term by sine squared. No, by cosine squared because we have tangent. That would have given us cotangent. So we're going to divide it by cosine squared. So we know anything divided by itself is 1, so cosine squared divided by itself is just 1. We know that sine divided by cosine is tangent, so sine squared divided by cosine squared is tangent squared. Not equal to tangent squared plus 1 is equal to 1 over cosine is secant, so 1 over cosine squared is secant squared. Okay, so even if you don't remember these trig identities, you can still calculate them. So if you had a cotangent and cosecant, then you divide each one by cosine, by sine, and that would have given you 1 plus cotangent is equal to cosecant. No, cosecant squared. Okay, so just like before, we know that x is equal to 3 times secant of 4 theta. We divide both sides by 3. We have secant of 4 theta is equal to x divided by 3. And since y is equal to 3 times tangent of 4 theta, and make that theta a little neater than that. We divide both sides by 3, then we know that tangent of 4 theta is equal to y over 3. Okay, now for this one, we know that since tangent squared of theta plus 1 equals secant squared of theta, and remember, if you wanted to, you don't have to do this step. This is more visual than anything. I don't need the bracket, just use parentheses. You can rewrite this as tangent of 4 theta squared plus 1 is equal to secant of 4 theta squared. But if you want to leave it as tangent squared of 4 theta, you can. Okay, well, we know that tangent of theta is equal to y over 3. That gives us y over 3 squared plus 1 is equal to, and we know that secant theta, or 4 theta, is equal to x over 3. That's equal to x over 3 squared. Okay, so if we simplify that, we know that y over 3 times y over 3 is y squared over 3 squared, which is 9, plus 1 is equal to x over 3 times x over 3, which gives us x squared over 9. Okay, so from here, we can just go ahead and multiply each term by 9. So if we multiply the first term by 9, the 9's would cancel out, leaving just y squared. Plus the second term, multiply that by 9. 1 times 9 is just 9. It's equal to, multiply x squared divided by 9. Multiply that by 9. The 9's cancel out, leaving just x squared. So if we subtract 9 from both sides, that gives us y squared is equal to x squared minus 9. And the very last step is we square root both sides. That gives us y is equal to, can't forget our plus minus, the square root of x squared minus 9. Okay. Now, if you wanted to, and I'm not sure if Newton will take it or not, but I'm pretty sure they would, you could have left it in this form. At least they used to do it. That still is a Cartesian equation, so. All right. So any questions on that one? All right. Oh, anyone still writing? Okay. All right, so let's say we know that if the curve on a plane is described by the parametric equations say x is equal to 1 plus sine of t, and y is equal to negative 2 plus cosine of t. So first, we want to know what point on the plane corresponds with t equals pi over 2. And B, we want to know what is the equation and shape for xy as t increases. Now with A, that's pretty straightforward. We know that x is equal to 1 plus sine of t. And we know that y is equal to negative 2 plus cosine of t. Now when t is equal to pi over 2, and that just means that x is equal to 1 plus sine of pi over 2. And y is equal to negative 2 plus cosine of pi over 2. So we know that x is equal to 1 plus sine of pi over 2, which is 1. And y is equal to negative 2 plus cosine of pi over 2, which is 0. So that means that x is equal to 2. Make that equal sign a little neater than that. There we go. I know that y is equal to negative 2. Okay, so we know that x equals 1 plus sine of t and y equals negative 2 plus cosine of t corresponds with the point 2, negative 2. Okay, so that x, don't even need the parenthesis there. X equals 1 plus sine of t. And y equals negative 2 plus cosine of t corresponds, make that e a little neater, to the point 2, negative 2. And t is equal to pi over 2. Okay. So really, this is just like the very first example where you just created your t chart and plugged in different values of t. We did the exact same thing there. And once you plug in your value of t, it gives you your xy, or your ordered pair. This is just another way that they would word it. And we'll do B on the other page. We're running out of room a little bit. Okay, so this one, we know that x is equal to 1 plus sine of t, and y is equal to negative 2 plus cosine of t. So if we subtract 1 on both sides of the equal sign, we know that x minus 1 is equal to sine of t. And for the other, if we add 2 to both sides, we know that y plus 2 is equal to cosine of t. Okay, so just like before, we want to remember that sine squared, and you can use whatever variable you want for that one, plus cosine squared is equal to 1. Okay, so sine squared, you can just rewrite that as x minus 1 squared, plus cosine squared, you can just rewrite that as y plus 2 squared is equal to 1. Okay, so you might be tempted to expand that and just make it x minus 1 times x minus 1 and then do the FOIL method. Same thing with y plus 2 squared. But you don't want to do that because in this form it's a lot more helpful. Okay. And it's helpful if you remember the equation of a circle. If you have x minus h squared plus y minus k squared is equal to your radius squared. Remember, that is the equation of a circle. It was centered at the point HK with a radius of r. So that means we just have to get this equation and put it in our equation of a circle form. That means we have x minus 1 squared plus, and instead of x plus 2, it has to be in the form of y minus k. And make that plus sign a little neater. Here we go. So instead of y plus 2, I'm going to put it in the form y minus negative 2 squared. And that's equal to, since it has to be in the form r squared, we can just make 1 squared. What I put y? I have to put 1. Duh. X minus 1 squared. Why did I even put y? So now that we have it in the right form, we just have to know that our h is equal to 1. Our k is equal to negative 2. And our radius is equal to 1. So if you had a radius of 9, and you, well, not a radius of 9, but if your r squared was 9, then you rewrite that as 3 squared, and your radius would have been 3. So whatever the squared value is, that's going to be your radius. Okay, so we know that those parametric equations gave us the equation of a circle centered at the point 1, negative 2 with a radius of 1. So it's centered at, remember, it's centered at the point hk, so it's 1, negative 2, where your radius is equal to 1. So if we decided to do a quick sketch of that one, nothing fancy. So x and y, there we go. Then our center, 1, negative 2, I'll say this is 1 and this is negative 2. Our center would be there. And our radius of 1 would go out to about here. Trying to draw it lightly first before I fill it in. There we go. So we have 1, negative 2, and the radius equals 1. And not really drawn to scale because that radius of 1 should take it up to negative 1, but I just drew it a little bit bigger so you can actually see it. All right, so any questions on that one? Okay, so I tried to look at all the different combinations of ways they could ask you a question and show you how, or the easiest way to approach it. So hopefully they don't come out with some different ones. right, anyone still writing? All right. And put these together now so they don't get mixed up. There we go. Okay, so now we're going to look at section 11.2, which covers the derivative and integrals of parametric equations. So what if we look at the tangent of parametric curves? Okay, so what if we let f and g represent two differentiable curves, which means their derivatives just exist, or it's a differentiable functions. Let's say functions, let's say equations. Where we know that x is equal to f of t and y is equal to g of t. So if we remember the chain rule, we could rewrite the derivative of y with respect to u is equal to the derivative of y, with respect to x. Instead of switching it up, I'll leave it like it would have been explained in Calc 1. That's the derivative of y with respect to u times the derivative of u with respect to x. Okay, so this was just how it was explained in Calc 1, but using it here, we can just say the derivative of y with respect to t is equal to the derivative of y with respect to x times the derivative of x with respect to t. So if we divide both sides by dx dt, and that means your derivative of y with respect to x is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. Okay. And this gives us the derivative of a parametric equation. Okay. Now for a second derivative, it says a little tweak to it. Okay. So we know that if we take the second derivative, we could just rewrite that as the derivative of the first derivative. Okay. So that means we can take our derivative with respect to x is equal to the derivative with respect to t divided by the derivative of x with respect to t. Which means that our derivative with respect to x of the first derivative is just equal to the derivative with respect to t. And you can put the dy dx on the side here, or just move it right on up. We get derivative of y with respect to x divided by your dx dt. Or you can just write it as a second derivative. The second derivative of y with respect to x is equal to the derivative with respect to t of dy dx divided by dx dt. And this is your second derivative of a parametric curve. Or parametric equation. Right. So let's say, for example, if we wanted to find the slope of the tangent line to the unit circle, x equals cosine of t, y equals sine of t, and the parameter t is from 0 to 2 pi. At the point t is equal to pi over 6. Okay, so we know that x is equal to cosine of t. Which means that the derivative of x with respect to t is just negative sine of t. And we know that y is equal to sine of t, which means our derivative of y with respect to t is equal to cosine of t. So if we wanted to find the slope of the tangent line, it's just the first derivative. Our derivative of y with respect to x, that's equal to the derivative of y with respect to t divided by the derivative of x with respect to t. Okay, well, our derivative of y with respect to t, that's cosine of t. And our derivative of x with respect to t, that's negative sine of t. Okay. But we know that cosine divided by sine is cotangent, so we could rewrite that as just negative cotangent of t. That means your derivative of y with respect to x is equal to negative cotangent of t. Make that x a little neater. Here we go. Now at pi over 6, where t is equal to pi over 6, the derivative of y with respect to x at t equals pi over 6 is equal to negative cotangent of pi over 6, which is equal to negative square root of 3. Okay, so since, just kind of give you a visual, So if we have our unit circle, there's not much of a unit circle, but our t is equal to pi over 6. At that point, the slope of the tangent line which I'll just say the slope of the tangent line is equal to negative square root of 3. And they may say the slope of the tangent line. They may say the instantaneous rate of change. They may just come out and say the first derivative. They're all the same thing. All right. Looks like everyone's done writing. Oh, still writing. All done? Oh, okay. Okay, so let's say, for example, if we wanted to determine the second derivative of the parametric curve defined by the equations x of t is equal to 2 times e to the power of negative 8t, and y of t is equal to 2 times e to the power of 5t. Okay, so before we can find our second derivative, we have to find our first derivative. So we know the derivative of y with respect to x is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. Okay, well, we know the derivative of y with respect to t is just equal to 2 times 5 times e to the power of 5t divided by the derivative of x with respect to t is just 2 times negative 8 times e to the power of negative 8t. Well, the 2's cancel each other out. So you can do that, or you could have made it 10 over negative 16 and cancel it out there, but easier to cancel out here. Okay, so that gives us 5 times e to the negative 5t power divided by negative, we can just bring the negative out to the front, 8 to the power of 8 times e to the power of negative 8t. We can actually simplify that, because remember, this one, x to the power of m divided by x to the power of n is equal to x to the power of m minus n. Make that a little longer. Which means that if we take e to the power of 5t divided by e to the power of negative 8t, that's equal to e to the power of 5t minus negative 8t. Which is e to the power of 13t. So we can rewrite our dy dx to equal negative 5 over 8 times e to the power of 13t. We can just put that right up here. Okay, so we have our dy dx. Now for our second derivative of y with respect to x. Remember, that's the derivative with respect to t of your dy dx divided by dx dt. Okay, well, we know our dy dx. So that gives us the derivative with respect to t of your dy dx, which is negative 5 times e to the power of 13t divided by 8, divided by your dx dt. We know our dx dt is, well, this is before we simplified it here, but it would have been negative 16 e to the power of negative 8t. Okay. So if we take this derivative with respect to t, we can go ahead and factor out the negative 5/8. So we have negative 5/8. So that leaves us with the derivative of e to the power of 13t, which is 13 times e to the power of 13t, divided by negative 16 times e to the power of negative 8t. Okay, so if we go ahead and simplify this by multiplying those two factors, we have negative 5 times 13 divided by 8, which gives us negative 65. Make that 6 a little bit nearer than that. Negative 65. That's even worse. Negative 65 divided by 8 times e to the power of 13t. And that is divided by negative 16 times e to the power of negative 8t. So we have a negative divided by a negative, which will give us a positive. We have 65 over 8 divided by 16. We could just write that as 65 over 8 divided by 1 over 16, which would give us 65 over 128. Okay, so now with these two terms, we can simplify this the same way we did it up here. We can just see that e to the power of 13t divided by e to the power of negative 8t is just equal to e to the power of 13t minus negative 8t. Which gives us e to the power of 21t. So combining these two will just give us e to the power of 21t. You can put it in front or you can put it in the numerator. Just a matter of preference. So that is our second derivative. All right, so any questions on that one? Okay, so we will go ahead and stop there only because the rest of these examples are 2 pages and longer, and I don't want to run over. So we will pick up at 11.2 tomorrow. Oh yeah, if you sent me an email over the weekend, I lost power from like Friday until Sunday morning, so I haven't had a chance to check them yet. So I will be checking them and responding to any emails that was sent. All right, you too.
Question.
Sure.
You say for the final, it's just like those final exam practices.
Yep.
Yeah, and it's the same for Calc 1. You said it's like you don't know for sure, but usually in the past it's like that, right?
Yeah, for Calc 1, it's pretty much,
Okay.
like I said, just from previous semesters.
Yeah, it's usually how it is.
I've had students say, okay, yeah, it was just like the
Yeah.
reviews.
Oh, it's like it's all new and too, like you said, right?
Yeah.
So it's basically.
Yeah, pretty much.
Yeah. Thank you. Have a nice day.
You too.
Have a good day.
You too. Alrighty, let me